Hello, everyone. I'm Dan from Xianjiaotong University. Today, I'm honored to introduce our work named Espresso, which can comprehensively reason about external routes using symbolic simulation. This is a joint work with Aaron from Colgate University. Network outages are common and costly, hitting the news again and again. Therefore, control plane verifiers are developed to proactively find misconfigurations before implementation. CPVs take network configurations and topology as input and check whether properties like reachability hold. Many outages are caused by link or node failures. As a result, many verifiers that can reason about failures are developed. For example, Minesweeper, Voyan, and SRE. Many other outages are caused by configuration updates. Accordingly, verifiers that can reason about configuration updates have emerged, like DNA. However, another less explored cause of outages is external routes. Reasoning about external routes is important, since external route-induced incidents can cause multiple issues. For one example, if a network leaks routes from one SP to another, it is at the risk of being a free transit between those two SPs, which will cause financial loss. For another, if a network's traffic is hijacked by another network, its private data is at risk. But reasoning about external routes is challenging, since the space of external route is classal. For IPv4, we have 2 power 33 minus 1 prefixes. And theoretically, each external neighbor can announce an arbitrary set of prefixes. There are 2 power 33 minus 1 prefix sets. For the whole space, suppose we have m external neighbors, then we have to multiply the number of prefix sets for m times. So how to handle such a classal space? One method is to enumerate concrete external routes, which is taken by verifiers like shapeshifter and backfish. However, enumeration is infeasible because of the huge space sets. Another method is to symbolize external routes using SMT, which is taken by NV, Minesweeper, and Backpack. Using symbolic external routes frees them from enumeration. But in practice, we found them unscalable, as the generated SMT constraints cannot be solved by SMT solvers in a reasonable amount of time. As existing verifiers are ill-suited to reason about external routes, we design and implement Espresso. We use this network to demonstrate the design of Espresso. It contains 2 internal routers A and B and 2 external routers N1 and N2. We use 3-bit IP addresses and prefixes for simplicity. And accordingly, we have 15 prefixes in total, and the space size is 2 power 30. In the network, router A and B pair with 2 SPs. Both of them permit 2 prefixes, 100/2 and 110/2 from the SPs. And router A sets the local preference of routes from N1 to 200 in order to prefer N1 as the exit to reach the internet. When designing Espresso, we have several observations. First, we observe 2 types of equivalence in the external route space. One is prefix equivalent, which means that prefixes matching the same or equivalent routing policies throughout the network will be treated the same during route computation. As in the example network, 100/2 and 110/2 are equivalent, and all other prefixes are equivalent. The other is advertiser equivalence, which means for a certain prefix, whether or not a neighbor advertises the prefix does not impact the best routes. As in the example network, router A sets the local preference of routes from router N1 to 200. Therefore, routes for prefix 100/2 and 110/2 from router N1 will always be selected as best routes, regardless of whether N2 advertises routes for the same prefixes or not. While the space size is as large as 2 power 30, there's only 3 equivalence classes. Therefore, we choose to follow the way of our prior work, SRE, which executes symbolic simulation to efficiently explore equivalences. This is the workflow of symbolic simulation, which takes configurations and topologies as input, and then executes symbolic route computation, symbolic packet forwarding, and property analysis. In symbolic route computation, SRE symbolizes the up or down state of links. It then executes a phase point algorithm to compute symbolic ribs, which contain failure equivalence classes. For example, NAC L1, L2 represents a failure equivalence class that contains 4 failure scenarios. For Espresso, we aim to symbolize external routes and compute symbolic ribs containing prefix and advertiser equivalence classes. A straightforward extension to SRE goes like this. We add dummy nodes for prefixes. Then we add a link between each external neighbor node and every prefix node. For each link, its up or down state indicates whether the external neighbor announces the prefix or not. Following SRE, we assign a Boolean variable for each link. The link states are decided by assigning 0 or 1 to link variables. And this way, we need 30 variables in total, where 15 is the number of prefixes and 2 is the number of external neighbors. However, for IPv4, we still need 2 power 33 minus 1 times m variables. Fortunately, we observe that prefixes are mostly independent in route computation. That is, the computations of routes for different prefixes do not interfere with each other. Consequently, we can first use 5 variables to select prefixes, 3 for IP address variables and 2 for prefix length variables. Then we use 2 variables to select external neighbors. This way, the selected links are represented by IP address variables, prefix length variables, and external neighbor variables collectively. As shown for router N2, the reusage of its neighbor variable, lowercase n2, is enabled by prefix independency. Using this encoding, we only need 7 variables in total. For IPv4, we can use only 38 plus m variables to symbolize the external route space of size 2 power 33 minus 1 power m. Based on the encoding, we illustrate symbolic route computation with the propagation of external route from N1. Here, lowercase n1 is the symbolic prefix, indicating arbitrary prefixes announced by router N1. We omit other route attributes for simplicity. Then the route propagates to router A, whose import policy only permits prefix 100/2 and 110/2. After going through router A's import policy, route 1 converts into route 2. The symbolic prefix changes to P1, L1, NAC L2, N1, resulting from intersecting the original symbolic prefix lowercase n1 with the disjunction of 100/2 and 110/2's Boolean representations. The propagation continues, and finally, the route passes the export policy of router B and is leaked to router N2. After symbolic route computation is symbolic packet forwarding. which contains first converting symbolic riffs into symbolic fibs, and then forwards symbolic packets to compute packet equivalence classes. However, when computing symbolic fibs, there's another challenge. Since in data plan, there are dependencies among prefixes. For example, symbolic prefix P1, L1, N1 contains 5 prefixes, 1/1 and 4/3. And the /1 prefix depends on all the /3 prefixes due to longest prefix matching principle. It indicates that 1 bit per neighbor is insufficient now. So does it mean that now we need 1 bit for each point in the space? Fortunately, the dependency is limited to prefixes having the same first bits but different lengths, and prefixes having the same prefix length are still independent. As a result, in data plan, we add a dummy node for each neighbor and prefix length. Then we use IP address variables and length-specific neighbor variables for encoding. Accordingly, when computing fibs, we have to convert control plane length and neighbor variables into data plan length-specific neighbor variables. And in this example, lowercase n1 is converted into 4 new variables. However, as L1 neg L2 indicates prefix length 2, only n subscript 1 superscript 2 is needed. This figure shows the symbolic packet forwarding beginning at router A. The symbolic packet is initialized with a symbolic packet header, true, which can match any forwarding rules. It then continues matching symbolic fibs and being forwarded until either arrive at the destination or exit the network or encounter a forwarding loop or black hole. The forwarding results in a symbolic packet exiting the network. For the symbolic packet header, P1 means prefixes whose first bit is 1. This Boolean formula containing length-specific neighbor variables means that the prefix length is 2 and the prefix is announced by N2 but not N1. And exit indicates the packet finally exits the network. After symbolic packet forwarding is property analysis. Espresso checks 5 properties, that is, route lead, route hijack, traffic hijack, egress preference, and block to external. Please refer to our paper for details about property definitions and checking methods. Finally, we will show the evaluation results of Espresso on a cloud service provider's one. The CSP's one contains 4 regions. Each region contains several peering routers, which peer with external neighbors. All regions are connected by a route reflector. We found route leads, route hijacks, and traffic hijacks on it. And I will show the details of a route hijack. It begins with SPA announcing a /31 prefix to PR1. Then the route is permitted by PR1's import policy, which is misconfigured, as it misses one deny entry in the prefix list to deny this internal prefix. The route's local preference is set to 200. At the same time, the connected route at PR2 is redistributed into BGP and propagated to the route reflector. Then, at the route reflector, it chooses the external route instead of the internal one because of having a higher local preference. Espresso finds the route hijack by finding this route in the route reflector symbolic rig, and it has been confirmed by the operators. This figure compares the running time of Minesweeper and Espresso to check route lead free from the CSP's one, where Minesweeper uses nearly 1 day and Espresso completes in 1 hour. Since Minesweeper uses a long time on the full topology, we use the 4 regions as macro benchmarks to compare Minesweeper and Espresso. The results show that Espresso is generally 1 to 4 orders of magnitude faster than Minesweeper. In summary, we first motivate the necessity of reasoning about external route. And then we introduce key points of Espresso's design. Finally, we show that Espresso finds real bugs on a cloud service provider's one. Okay, that's all for my presentation today.